Morning, student. Welcome to today's physics class, 11th physics. I am excited to dive into a crucial topic in the mechanics of solid stress strain Hooke's law. Okay, so now let's start with a quick story about the man began one of our key concepts, Robert Hooke. He was a brilliant scientist and a contemporary of Sir Isaac Newton, who was not just a physicist. He was an architect, surveyor, microscopist. He was one of the first people to look at a cork under the microscope and describe the tiny boxes as cells. But in 1678, he published the anagram that when solved, read the Latin phrase name as the extension. So the force as the extension. So the force. This simple statement is the essence of what we now call Hooke's law, a principle that governs the elasticity of every solid structure around us, from the spring in your pen to the gables of biggest bridge. We will explore exactly what that means today. Okay, right. So let's look at the three main ideas we will be discussing. I am going to use my whiteboard to quick summary. So when an external force acts on a body, acts on a solid body, okay, two things happen. One is an internal resistance develops. Internal resistance develops. Second one, change in shape occurs. Okay. So when an external force acts on a solid body, two things happen: an internal resistance develops and a change in shape occurs. So first of all, stress. Sigma. This symbol means we can call it as sigma. Okay, stress. This is a measure of the cause. Measure of the cause. It is the internal restoring force developed per unit cross-sectional area. Okay, it is the internal restoring force. Internal restoring force developed per unit cross-sectional area. Think of it as a material's internal resistance to the deforming force. Okay. So formula F is equal to, sigma is equal to F by A. This is a formula for stress. Sigma equal to force by area. So nothing but F by A. SI unit Newton per meter square or Pascal PA. Okay, Pascal. Next one, strain. Strain. We can call it as a epsilon. Okay. So this is a measure of the effect. So stress is the cause, strain is the effect. Okay. It is a measure of the effect. It is a relative deformation produced. Okay, it is the relative deformation produced. It is a ratio of ratio. Sorry. It is a ratio of change in dimension by original dimension. Okay, original dimension. It is a relative deformation produced. It is the ratio of the change in dimension to the original dimension. So original dimension means original length. Okay, L. So change means del L. So del means change. Okay. So change in dimension by original dimension. This is the F sharp. This is the strain. Okay. Clear that? So SI unit. It is the unitless or dimensionless quantity. Okay. It is a unitless or dimensionless because it is a ratio of two similar quantity. For example, length by length. So it is a unitless or dimensionless. Okay, right. Then third one, Hooke's law. Hooke's law. It is a relationship between the two before strain and the stress. Okay, this is a relation between the previous two. So it said that stress is directly proportional to the strain within the elastic limit, but only within the elastic limit. So stress sigma is directly proportional to the epsilon within the elastic limit. So this means if you double the stress, you double the strain. Stress means force, deforming force. It's a cause. Strain means change in length by original length. So if you double the stress, you double the strain up to a certain point. Clear? Okay. So what we define the stress? Stress means internal restoring force developed per unit cross-sectional area of a body due to the external deforming force. When an external force acts on a body, it causes a deformation. Yeah, which in turn leads to an internal force within the body to attempt to restore its original state. Yeah. So sigma is equal to F by A, Newton per meter square. Strain. Next one, strain. Strain is the measure of the deformation produced in the body. Measure. Stress is a cause. Yeah. So measure of the cause. The strain is a measure of the effect. So deformation produced in the body. It is a defines the ratio of the change in dimension produced by the external force due to the original dimension. Okay, and it's epsilon is equal to del L by L, unitless, dimensionless. Next one, Hooke's law. Hooke's law is a fundamental principle of physics that governs the elastic behavior of the solid. It said that within the elastic limit, the stress applied to the body is directly proportional to the strain produced in the body. Clear? So stress is directly proportional to strain. Okay. Now we will see this in action. I will share the screen once again. Okay. So please look at that screen. We are on the FET Hooke's law simulation. We have a intro tab here. Okay. Click that. We have a simple spring. On the left, we have a scale to measure the spring force, that is applied force, spring force, displacement, equilibrium position, and then values. Clear? So, equilibrium position. So, equilibrium position, this is our 0 point. This is our 0 point. When there is zero force, so there is zero extension. Clear that? Now, I am going to apply a small force like that. Now I am going to apply a small force of, for example, we can, we can take as a 10 Newton, like that. Yeah. So the spring stretched by a certain distance. Okay. And I am going to apply another force of, like, for example, 50 Newton. Okay. The spring has stretched by a certain distance. Let's call that distance, for example, we can take it as a x1. We are applying a deforming force of 50 Newton. We are applying a deforming force of 50 Newton. Internally, the spring developed a restoring force. The spring developed a restoring force. So 50 Newton. Yeah. The spring developed a restoring force. That is, that force exactly balances the 50 Newton applied force. So here also 50 Newton force, which is the restoring force. Yeah. So this internal restoring force per unit area is what we define as a stress sigma. Yes, correct. This is a sigma. This is the applied force. So this is a sigma. This is what we define as stress. Now look at that stretching distance. The relative change in length, or how much is stretched compared to original length, that is equilibrium length, equilibrium position. This is our strain epsilon. Okay. The distance, you can see that 0.250 meter. The distance you see is directly proportional to the delta. That is, this is delta directly proportional to the strain formula. Clear? So, if you apply a higher forces, stretching also increases. That is, change in length also increases. So, stress, applying a force, strain, changing in the dimension. So, stress is directly proportional to strain. So, in 50 Newton, you can see that 0.25 meter. Yeah. For 100 Newton, you can see that exactly double. Yeah. 50 Newton into 100 Newton. So, strain 0.500 meter. Okay. Right. So, this is a Hooke's law. If you double the force from 50 Newton to 100 Newton, what do you predict will happen to the extension? Yes. So if you apply the force to 100 Newton, the extension has indeed doubled from 0.250 meter to 0.50 meter. So x2 to x distance. Yeah. So since force is proportional to the stress, yeah, force is proportional to the stress, and the extension is proportional to the strain. Yeah. So you can see that also. This is a equilibrium position, and if you compress the spring, now applied force towards the wall, but the restoring force against the wall, that is away from the wall. Yeah. Clear? So force is proportional to the stress. and extension is proportional to the strain. This is a direct observation here that stress is proportional to the strain. This is the Hooke's law. Now, I will click the swing constant. For example, okay. Okay. Now I will click the spin constant here, the slider, and make the spin stiffer. That means larger K. For example, 50 Newton, 0.250 meter. For the swing constant, 200 Newton per meter. Now I will increase the spin constant. That is, I make the spin stiffer. That is larger K. You can see that. Yes. For 500 Newton per meter swing constant, distance 0.100 meter only, because the spin stiffer here. Yeah. Now I reapply the 100 Newton. 100 Newton. Yeah. Notice the extension is much smaller before the previous case. That is in terms of spin constant 200 Newton per meter. For the applied force 100 Newton, the extension 0.500 meter. Now, for the swing constant 500 Newton per meter, the applied force for the applied for 100 Newton, the extension only 0.200 meter. That is, the extension is much smaller. So, a stiffer material has less strain for the same stress. A stiffer material has less strain for the same stress. This difference in stiffness between the material is what determines if a material is good for a crane like a steel or good for cushioning like rubber. Okay. So this difference in stiffness between material is what determines if a material is good for crane or good for cushioning. So the simulation confirms F directly proportional to the extension. In our class terms, stress is proportional to the strain. Okay, right. Let's now use this understanding to solve some problems. Clear? So I will show the sum. So this is a problem number 1. Calculation of stress and strain. A metallic wire has a original, that is L, of 2.5 meter and diameter D 2 millimeter. It is subjected to a stretching force F of 157 Newton. If the extension del L produced in the wire is found to be 0.05 centimeter, yeah, determine the tensile stress and longitudinal strain. Okay, determine the tensile stress and longitudinal strain. So already we know that stress and strain. But what is tensile stress and what is longitudinal strain? Yeah. So let's apply these formulas, stress and strain to the problems. Okay. Right. So original length 255 meter, diameter 2 millimeter, force 157 Newton, extension 0.05 centimeter. Okay, clear? So we have to convert millimeter to meter. For example, 2 millimeter. So 2 into 10 power 3, 10 power minus 3 meter. Clear? Okay. This is a diameter. So radius half of the diameter. So 1 into 10 power minus 3 meter. Clear? Extension in centimeter. So we have to convert into meter. 0.05 into 10 power minus 2 meter. So we can write as 5 into 10 power minus 4 meter. Okay. So this is the extension. Okay. Now, tensile stress is nothing but stress. Okay, stress sigma is equal to F by A. Clear? So A means cross sectional area of the wire. Okay, so we know that formula for area, that is pi r square. So F by pi r square. Okay, right. Now sigma is equal to F by pi r square. F 157 Newton. Pi r square 3.14 into 10 power minus, because 1 into 10 power minus 3 becomes as so 1 into 10 power minus 6. So we can neglect 1. Yeah. So like that. 3.14 into 10 power minus 6 meter square. So sigma, we can divide the 157 by this number. We will get the 50 into 10 power 6. This minus 6 goes here. So 10 power 6 Newton per meter square, or 5 into 10 power 7 Pascal, because stress has a unit in terms of we can write as a Newton per meter square or Pascal, because stress is nothing but pressure. Yeah. So pressure also we can write unit Pascal. Yeah. Okay. Right. So this is a tensile stress. Next one, longitudinal strain. So longitudinal means change in length. It denotes a length. So longitudinal strain means nothing but strain. So epsilon del L by L. Del L. Already we have a del L. So 5 into 10 power minus 4 meter. This is a in term extension in terms of meter. So 5 into 10 power minus 4 meter. Yeah. Right. And the length, original length 2.5 meter. So then we will get the 2 into 10 power minus 4 unitless. So meter cancel. So unitless. 5 by 2.5, we will get the 2. Yeah. So epsilon is equal to 2 into 10 power minus 4 unitless. Clear? This is a sum 1. Clear? Now we will move into the next sum. This is the next sum. Problem number 2. The calculation of the maximum force load. A steel cable for a small crane has a radius R of 2 centimeter. The engineering specifications require that maximum stress sigma maximum in the cable must not exceed 1.5 into 10 power 8 Newton per meter square. Then what is the maximum load force that cable can safely support? So this is a second sum. Another one important sum. Calculation of maximum force. That means load. So cable must not exceed 1.5 into 10 power 8 Newton per meter square. What is the maximum load force? Okay. We will solve this sum. Okay. Next. So we have a radius 2 centimeter. Yeah. So we have to convert into meter, 0.02 meter. Okay. Then second, sigma max. Maximum stress 1.5 into 10 power 8 Newton per meter square. What is the maximum safe load? That is force. F max the cable can support. Yeah. So we can use the stress formula, but this time we solve for force. For example, sigma is equal to F by A. From this formula, we will get the F is equal to sigma into A. Yeah, sigma into A. A means area, so pi r square. Sigma into pi r square. And sigma maximum stress 1.5 into 10 power 8 Newton per meter square and pi r square 3.14 into 0.02 square like that. Okay, 3.14 into 0.02 meters square. So we can write the unit also here like that. Okay, so F max 1.5 into 10 power 8 Newton per meter square into pi r square. So 3.14 and 0.02 the whole square gives 0.0004 meter square. Okay, 0.0004 meter square. So which gives 1.256, 3.14 into this number. So which gives 1.256 into 10 power minus 3 meter square. Right? So we can cancel the meter square. 1.5 into 1.256, which gives approximately 188,400 Newton. Okay, you can write. So which gives approximately 188,400 Newton. Okay, right. So this real life example shows how engineers use the concept of maximum stress to design cranes and structure for safety. If the load exceeds 188,400 Newton, the cable will be stretched past its safe limit, which could lead to failure. Okay, so that cable must not exceed this load. Yeah, 188 for this case, 188,400 Newton. If the load exceeds this value, the cable will be stretched past its safe limit. Yeah. So which could lead to failure. Clear? Okay. So now it's a time for quiz. I will share my screen now. Okay. The quick quiz. Okay. First of all, what is the formula for tensile stress? Already I told you, tensile stress is nothing but stress. Yeah. So sigma. Yes. Yeah. Option B. Sigma equal to F by A is the correct answer. Clear. Very good. Next one. Strain. Strain is a dimensionless quantity, force per unit area, unit of Pascal, proportional to force on T. Yes. Option A. Dimensionless quantity. Yeah. Okay. Very good. Third one. The elastic limit is the point beyond which. So elastic limit means the material breaks immediately. The material does not return to its original shape. Stress becomes zero. Strain decreases. So here, within the elastic limit means the material does not return to original shape. Option B is the correct answer. Okay. And the fourth one, the SI unit of stress is equal to the SI unit of which physical quantity? Already I told you the stress unit for stress is a Newton per meter square or Pascal. So that unit which is equal to the SI unit of which Pascal physical quantity? Option A, work, energy, pressure, force. Pascal means, yes, pressure. Option C is the correct answer. Okay. And the final one, in real world applications, Hooke's law is crucial for designing suspension bridges because it ensures the cable deform permanently under load. Stress and strain remain proportional to the elastic limit, preventing failure. Strain is always greater than the stress. The material becomes more rigid over time. In real world application, Hooke's law is crucial for designing suspension bridges because it ensures, yes, option B is the correct answer. The stress and strain remain proportional up to the elastic limit, preventing failure. So we can see the answer key. What is the formula for strain stress? Sigma squared F by A. Strain is a dimensionless quantity. Elastic limit is the point beyond which the material does not return to its original shape. Okay. The SI unit of stress is equal to the SI unit of which physical quantity? Pressure, because Pascal. Yeah. And the final one, in real world applications, Hooke's law is crucial for stress and strain remain proportional to the elastic limit, preventing failure. Clear? Okay, good. Yes. So now is time for quick summary. Let's quickly summarize the key takeaways on the whiteboard. So today we learned the elasticity. So the elasticity means the ability of the material to recover its shape. Okay. So sigma, internal resistance, force by area. Internal resistance, force by area, Newton per meter square Pascal. Strain is a deformation. So del L by L. It is a unitless. Hooke's law. It is stated that stress is that directly proportional to strain. For a small deformation up to the elastic limit, yeah, stress is directly proportional to strain. So this principle is vital in engineering design. Okay. So your homework has two parts. I will share the screen. Please take the screenshot or take down. Write this down. Okay. I will. So this is your homework. It has two parts. One is conceptual homework, another one numerical homework. First one, a student performs an experiment on a rubber band and a steel wire of the same length and thickness. Which material will show a much larger extension for the same applied force? Okay, rubber band and steel wire, same length, thickness, same force, same applied force. So which will show a much larger extension? Okay, explain your answer by the defining the time stress, strain, elasticity. Clear? And numerical problem, numerical homework. A force of 49 Newton is applied to the wire of length 1.5 meter and the cross-sectional area 2.0 into 10 power minus 6 meter square. So this force causes the wire to extend by 0.05 centimeter. Calculate the following. The tensile stress, sigma developed in the wire, and the B. The longitudinal strain produced epsilon produced in the wire. Very simple one. Yeah. A force of 49 Newton, length, cross-section area. So this force causes a wire to extend by 0.05 centimeter. Calculate the following. The tensile stress developed in the wire and the longitudinal strain produced in the wire. Clear? Okay, good. Okay, right. So the ability of a material to recover its shape is called elasticity. When a force is applied, the material internal resistance is measured by stress, which is nothing but force by unit area Newton per meter square. The resulting deformation is measured by strain, which is epsilon. It's the ratio of del L by L. Original change in length by original length, which is making it unitless. Finally, Hooke's law states that for a small deformation, stress is directly proportional to strain. So sigma is directly proportional to epsilon or to the elastic domain. Okay. So that's all for today. Thank you. Jai Hind, Jai Vidya Siddhi, Jai Bharat. Thank you, teachers and students.